Welcome to a video on section 6.2, the indefinite integral and anti-differentiation using substitution. We'll be covering pages 2 and 3 since we have completed page 1 in class. So on beginning of page 2, we see a list of integral formulas. And so really the best way to think about it is to think of the derivative and going backwards. We start with some of the trig ones, like cosine x. The antiderivative of cosine x is sine x plus c, because we know that the derivative of sine x is cosine x. And of course, the derivative of constant is 0. Whereas for number 2, the antiderivative of sine x is cosine x plus c. And again, these are all indefinite integrals. So they represent a family of solutions with a constant being added at the end. For secant squared, hopefully you remember that the derivative of tangent is secant squared, so the antiderivative of secant squared is tangent x, of course, plus c. For cosecant x, that'll be cotangent x. The derivative of cotangent is negative cosecant squared x, so that's why we have the negative there. And that's actually my dog Harrison barking. I'm not sure why he's barking. Anyway, the derivative of secant is secant x tan x. So that's why the integral, or the antiderivative of secant x tan x is secant x plus c. And lastly, we have negative cosecant x. We'll go back to the table up top. So we know that if you have x squared, that derivative is, of course, 2x. So when you take the antiderivative of 2x, of course, that's going to be x squared. What we notice is that we're adding 1 to the exponent and dividing by the new exponent. So in essence, when you antiderive a power function like x to the n, it's going to be 1 over the n plus 1 times x to the n plus 1 plus c. So basically, you're raising the exponent by 1 divided by a new exponent. However, when you have x to the negative 1, that instead will be ln x, and it's going to be the absolute value of x plus c. Oh, by the way, for power formula number 1, that's assuming n does not equal negative 1, because when n does equal negative 1, we do what we do in the second formula. The integral of 1 over x times dx is natural log of absolute value of x plus c. For inverse trig formulas, hopefully you recognize, sorry for the Facebook notification there, that we have 1 over root 1 minus u squared is the inverse sine of u plus c, because derivative inverse sine of u, and it could be any letter, remember. The letter here is always arbitrary, but it would be inverse sine of u plus c. This one will be inverse tan of u plus c. And of course, this one's inverse secant of u plus c. And of course, if you add negatives next one, then you do their complements like cosine, cotangent, or cosecant. And then for this one here, that's e to the x plus c. We did this in the previous page, x ln x minus x plus c. For a to the x, it's 1 over ln a times a to the x plus c, because the derivative of a to the x, remember, if we have this, the derivative is a to the x times natural log of a. So we kind of do the opposite. Instead of multiplying by natural log of a, we divide. And then this one here, it's a little tricky. But it's going to be 1 over natural log of e, x times natural log of x minus x plus c. The reason why that works the way it does is that we can rewrite the log in this manner. That's using change of base formula. And because ln a is a constant, like we pulled out, And we know what the antiderivative of natural log of x is. Now we know it's just x times ln x minus x and then plus c. All right, let's look at example 2. So f of x equals x squared minus 1, let u equal x cubed, find each of the following. Well, a is easy. We're integrating x squared plus 1 times dx. Make sure you put the x squared plus 1 in parentheses. So that way you're showing you're doing the antiderivative of that whole expression. Of course, that's x cubed over 3. Because you add 1 to the exponent, divide by the exponent, plus x plus c. For part B, so f of u, that's interesting. F of u is going to be u squared plus 1. And since u is x cubed, that's x6 plus 1. Or, if we leave it in terms of u, u cubed over 3 plus u plus c. And then f of u times dx. So, in this case, actually, before I do that, let me substitute x cubed for u. So it'll be x to the 9th power over 3 plus x cubed plus c. Lastly, for part C, f of u times dx. Remember, f of u was u squared plus 1, but it's also x to the 6th plus 1. So it's x to the 7 over 7 plus x plus c. Now, the reason why we have these, it's very important you pay careful attention to the differential, the du and the dx. So C, we had to have it in terms of x because we were taking the antiderivative with respect to x. For B, we left it in terms of u, and then we substitute afterwards. And of course, we got two very different answers for B and C. So the moral of the story is pay close attention to dx and du. Okay, let's look at page 3 now. So again, the dx is called the differential, and du is also called the differential. And in fact, that would make sense because dx is canceled. So, du does equal du over dx times dx. Now, why is that important? Well, let's take a look at example 3 here. So, dy over dx equals 14x times e to 7x squared. That was one of the examples in section 6.1. So, what if I decided to rewrite this integral in this manner? Yeah, that's fair treatment. I'm just, rearranging some things here. And what if I decided to let u equal 7x squared? Well, if that's the case, if I take the derivative of both sides with respect to x, of course du over dx equals 14x. So, and if I multiply both sides by dx, I get this. So let's bring it back in. I see right here, that's just what du equals. So that's the integral of e to the u times du, which of course is just e to the u plus c. Or if I replace u with 7x squared, bring that back in. you get e to the 7x squared plus c, which is what we know to be the antiderivative of 14x times e to the 7x squared. We did that in section 6.1 notes. Also, if you take the derivative of e to the 7x squared plus c, you do get 14x times e to the 7x squared. So essentially what we did was we realized that 14x is a derivative of u. So du equaled u prime times dx. That's how this was actually useful here. Because then we were able to substitute for this portion into our integral and actually make this an easier problem to work out. Let's try this again. And this is called antidifferentiation using substitution. Let's say u equals 1 minus 2x to the fifth. Then, of course, du over dx equals negative 10x4. Or du equals negative 10x4 times dx. So I'm going to do a little rearranging here. 1 minus 2x to the fifth raised to the 1/2 times 7x4 times dx. I'm going to move the 7 off to the left as a constant. So now I have this. And if I divide both sides by negative 10, I see that, oh, I could replace x4 times dx with d over negative 10. And 1 minus 2x to the fifth is u. So I got negative 7/10 times the integral of u to the 1/2 times du. So negative 7/10 times u to the, excuse me, 3/2 over 3/2 plus c. And I could flip over to 3/2, have negative 7/10 times 2/3 times u to the 3/2 plus c. If I keep going around, negative 7/15 times u to the 3/2 plus c. And of course, u is 1 minus 2x to the fifth. So that would be the antiderivative for 7x4 times square root of 1 minus 2x to the fifth times dx. Now, if I'm saying y equals this, the derivative of that, of course, would be negative 7/15 times 3/2 raised to the 1/2 power, doing my chain rule. And if I kind of work things out, I get negative 20 over 30 times negative 10x4 times square root of 1 minus 2x to the fifth. And things kind of cancel, and we actually get what we're looking for. So let's try one more. Let me change colors. We'll go red. Usually you want to let u equal the expression with the larger exponent, because then when you take your derivative, without getting that, and by the way, I could probably factor out a 2 from that. And simultaneously multiply both sides by dx. So du over 2 equals 3y to the fifth plus 5y. Oh, sorry. That's why I got to pay attention to the variables. I meant to say dy. Yikes. Even I make those mistakes. There we go. So we see that that's just going to be du over 2. That portion right there. That's why this is called integration by substitution. So I have 10 u to the 7th times du over 2. 10 over 2 is 5. And I can pull out to the left. And then I take the antiderivative, so u to the 8th over 8 times 5 plus c. And of course, u is y6 plus 5y squared minus 3. So 5, so y6 plus 5y squared minus 3 raised to the 8th power all over 8 plus c. You can take a derivative of that to check to see if it works with respect to y, but yeah, just trust me, it works. So I think that kind of takes care of stuff I want to do in this video. So now you're prepared to do some of the bookwork, and we're all set for the video. I'll see you guys later.